Okay guys, we'll be going over initial value problems in the context of differential equations. Here we're given that dy dx is equal to 15x minus 7, and we're also given a set of points where x is 0 and y is 4. So let's get that out of the way for clarification, and let's think about where do we begin. First off, we want to set up this equation such that it's y equals to find the general solution. So where do we begin? Let's multiply the whole system by d of x. You will notice that the d of x cancels on the left side of the equation, and from then on out, it's this right here. Now we have to get rid of the d's, and to do that, we'll have to integrate. The integral of dy is simply y, and the integral of 15x is simply you add 1 to the exponent and divide by the new sum of the exponent. And the integral of a constant, slap on the integral with respect to a certain variable. And of course, you gotta write your constants since we're dealing with indefinite integrals. Now, we can actually do something with the constants. We don't really need them in this kind of setup. When we put two constants together, what ends up being the output? Turns out it's just another constant. So this is our general equation, but we're not quite done yet. We still gotta find out what c really is. And that's what we're given the set of points. And to do that, it's all a matter of direct substitution. So let's see, 15 times 0 is 0, anything divided by 0 is 0, and anything multiplied by 0 will be 0. So we now have confirmation that c is going to be 4. Now that we have the identity of c, we can just plug back into a general solution. And what was once the general solution is now the particular solution, which is what you need to answer initial value problem. Okay, so in this example we have dy over dx is equal to 2x times y, and when x is 0, y is 3. So, first things first, let's multiply the entire system by d of x. When we do that, we get dx on one side, but we still have y on both sides. So, what can we do? Let's multiply the system by 1 over y. As a result, when we do that, we get our y's with y's and our x's with x's. Now we can find the counter derivative, or in this case, we can integrate the whole system. When we do that, the integral of 1 over y is the natural log of y, and you can just apply the power rule for 2x. Did I really leave the 2's in when I could just cancel them so apply it further? Yes. And you will see that I already moved our constants to one side when we do the integrals, and we're not quite there yet. We haven't really found the general solution. What we can do is, because of a natural log of y, we'll exponentiate both sides. In this case, we're raising everything, or we're having e as a base, because the e constant of the natural log cancel out. So we have our general solution where y is equal to e to the power of x squared plus c. Now, if you don't like this notation of general solution, I totally get that. And there's one way to actually make it, well, simpler. So let's recall the property of exponents, where you have the same basis but different exponents, and you're multiplying them. You'll notice that the output is simply the same base but with the sum of the exponents. It also works backwards. So, how can we apply this to our general solution? Well, we can actually break e to the power of x squared plus c into, well, a product, where we have the following. Now, what happens when e is raised to the power of some constant? Do keep in mind that e is a constant raised to another constant. And it turns out that it's just c times e. to the power of x squared. And this is our general solution in its simplest form. Now, we still gotta plug in our points for when x is 0 and y is 3. So let's do that through direct substitution. Well, we got 3 is equal to c times e to the power 0 squared. 0 squared is going to be 1. E to the power 0, like any number, is going to be 1. So as a result, we get 3 is equal to c. So we have the identity of c. We just got to plug into the general solution to acquire the particular solution. And that's how you go about solving an initial value problem.